Hi, my name is Jahana Ramir and welcome to Lab 5 Magnetic Braking with Faraday. The purpose of this lab is to investigate Faraday's law, which relates time-varying magnetic fields to a Curly electric field, whose path integral around a closed path provides an EMF that can drive current. We collected observational data of a magnet falling through a conductive tube of aluminum foil and utilized Python to model the magnet and tube interaction computationally and compared the model to empirical results. Some of the fundamental principles used in this lab was Faraday's law, which is a basic law of electromagnetism predicting how a magnetic field would interact with an electric circuit to produce an electromotive force EMF, a phenomenon known as electromagnetic induction. Related to Faraday's law, Lenz's law was also used, which states that the direction of the electric current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes charges in the initial magnetic field. Cloud-Support law was also used, which describes the magnetic field generated by a constant electric current. It relates the magnetic field to the magnitude, direction, length, and proximity of the electric current. Newton's second and third law was also used. Newton's second law states that the acceleration of an object depends upon two variables, the net force acting on the object and the mass of the object. His third law states that for every action in the nature, there is an equal and opposite reaction. Now onto the process of the experiment. In this experiment, we marked the north pole of the bar magnet and hold the tube of aluminum foil vertically. We began recording a video of the full tube and dropped the magnet through the tube. We reviewed the video footage to find when the magnet enters and leaves the tube, and we calculated how long it was in the tube. We repeated this procedure 1 to 4 times and calculated the average time it takes for the magnet to fall through the tube. These are my results. My average time for the video was 1.32 seconds with a total runs of 5. Now onto computational model. We started off with the physical constants and then the geometry of the tube. We calculated the magnetic field of the bar magnet next. Lastly, with the defined calculator, LUX data analytic is where we calculated the d flux over dt through each ring due to the falling magnet. Next, we calculated the gravitational force on the magnet, and then we calculated the magnetic force from the tube of the magnet, and then we created a vector for the magnetic force on the magnet. Lastly, we updated the magnet's velocity and position over time. This is the computational model that I got with an average time of 1.29 seconds. So the first question asked was, what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? So if the resistivity of the conductor were reduced as close as possible to 0, the induced current in the tube would be larger due to Ohm's law, which would in turn cause the magnet to take longer to fall through the tube if the resistivity was close to 0. It's possible that the braking force would cancel out the force of gravity and the magnet would stop falling altogether. The second question was, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes or slots were cut into the tube, the magnet would fall through the tube faster because the flow of current through the tube would be disrupted. Thank you for watching, and I'll see you on the next lab.